Yeah, so what we defined was mainly this algebraic construction inspired by geometry, localization. Right, so you can localize by a multiplicative set, which means introduce fractions in the set big T, and even more special, you can take prime ideal P, and then the big set T will be complement of this, which is A minus P. That's a multiplicative set. You invert all those elements. That is called localization of a ring at a prime ideal. Localization of A at P. That is how you get these restricted fraction integers. So for example, you can decide that you will divide only by odd B. So you will not have half, but you have everything else. You will have by 3 or by 5 and so on. You won't have by 6, for example, but by 7 you will have. Then there are projective versions of this, and we defined this OX functor. So this is especially good for morphisms. So when you want to compare variety X with variety Y, then instead you should compare OY with OX, and the arrow will be reversed. Okay, so this is a contravariant functor. We'll be using this all the time. We define distinguished open set X sub f for a polynomial. It's basically the zeros of f complement in the variety X, and this can be used to cover any open set that we had seen, and we also saw algebraic version of it. So OX functor on this distinguished open set basically localizes your polynomial ring. It localizes it by multiplicative set powers of f. So 1 by f gets introduced essentially in the ring. And finally the germs are germs of over the variety X at the point P is basically the polynomial ring localized at the maximal ideal, which means that anything outside the maximal ideal can be now inverted, which makes sense because these are nice functions defined around at the point P. The fractions are defined. Okay, so now what we will do is we will define a more, we'll basically relax some of the axioms in a morphism. So this will be a new way to compare two varieties. So this arrow we will call the rational map arrow. The definition will be kind of the opposite that we gave for morphism. So we said that morphism is a map which for any open set V of Y gives in the pre-image an open set and so on, right? Instead now what we will do is we will take an open set U of X and start the definition from that. So for varieties XY, a rational map phi from X to Y is given as, take any set U, open set U of X, and a map defined on that. So U is open in X and phi U is a morphism. Okay, so what we want is we want now to start with the open neighborhood inside X, and we just want a morphism from that neighborhood to Y. So it's a more local property than what we had in morphisms before, because morphism was kind of working with the whole of Y. Instead of this, now we have whatever the image of U is under phi U, only that part is being used in this. And yeah, this set may be too big because there are, open set U may have a subset which is also open, like U prime and so on. So we want a notion to compare there. So we mod it out by the equivalence relation with the understanding that if phi U and phi U prime are the same on U and U prime, U intersection U prime, then we call them the same. Okay, so if in a small enough open set you have equal morphisms, then you call these pairs as equal in the set. Something that we have been doing with rational functions all the time, so the same thing, where U phi U is considered equal to or related to formally V phi V if phi U is equal to phi V on the intersection, which is again an open set of X. This is happening in X. Okay, so with that we have these in fact, if we took Y to be X, what will happen? What are these objects U comma phi U going from X to X? So in that case, I think you will recover the definition of rational functions if you are mapping points of X to itself. But if you map from X to Y, where Y is some arbitrary variety, then we call it a. That is true, yes. Okay. Yeah, maybe I should write that. Field meaning that it's a line. A1. Gives back the definition of Kx. Okay, but now this allows us to actually compare two very different varieties. Y may not be a line, may not be the affine line. And we will call this rational map to be dominant if it kind of covers everything in the image. So rational map phi is called dominant if there exists an open U such that the corresponding map from U to Y is dense in Y. So I have to define this term in case you don't know what dense set means in a variety. We basically want to say that it's almost everything. So image of phi U inside Y is almost everything in Y. Okay, in particular if phi U is Y, then we will say that the map phi is a dominant map.
Should we think phi U as a restricted map on U or?
No, there is no phi. Okay. What is the relationship between phi and phi U? Yeah, you can think of it. Sure, it's a restriction. Yes.
If X is also open in X, then automatically we have the phi defined. Then why are we doing so much?
No, the thing is phi need not be defined on all of X. It's only defined on some open subset.
Correct.
For all open sets, right?
No.
Only some.
But there is no common.
Not for all.
Yeah, so not for all, no, it is for every u.
Then you have a phi on X.
It is on every u, but the thing is, what name will you give phi? It's not a morphism. It may not be a morphism. It's just a map.
You're saying for all X is open in X.
Yes.
For all open in X, open in U, we have defined a morphism.
Yes.
So there is phi X entire, and if U is a subset, we're saying that phi U is just a restricted map.
I don't think you want all open sets. It's a morphism on some open set.
No, but the definition is this. I'm looking at all the pairs.
It can't be all. Because then you just have a morphism on X. You want something that is not a morphism on the whole of X.
Okay.
So you want a morphism only on some open subset U in X.
Oh, so you are saying that it should not be this set.
It should be all the opens.
Okay.
Be some collection of opens over where it's a morphism.
But then just one may be enough.
Yeah, just one is enough. But you still have the equivalence relation.
So what should I say? Some open u. Yeah, this I have to clarify it next time. I see the problem. Yeah, I want this rational map to be much more relaxed than morphisms. So I cannot take u to be x, otherwise it will be the same thing as morphism. Yes, so even if this map is not defined on the whole of x, it will be enough it is defined on, let's say, even a single neighborhood. If it is defined, then we are fine. And yeah, so why does that make sense? I'll motivate that pretty soon. Essentially, there is this idea of dense sets, and even if we don't cover the whole variety, we'll be happy if we are able to cover most of it. So what is the meaning of most? So let's define that. So W, a subset of X, is called dense if the smallest closed set containing W is everything. Okay. So in other words, geometrically, so in the real plane, for example, you have this W as an open ball. Okay, and what is the smallest closed set which contains this ball? So you have to grow it slightly bigger. Basically, you introduce the limit points or the boundary. So this will become slightly bigger. We'll be including this limit points, right? So this will be the closed set, which clearly is still small. In the Euclidean plane, this is still a very small part of the Euclidean plane. Now you'll be surprised to know that that doesn't happen in our case. So in the Zariski topology, if you take an open set and you close it, you get everything. Okay, so our open sets are truly large. Let's prove that.
So one thing, can you show the definition dominant?
Oh, dominant is just that image is dense.
Phi of U is
Yeah, phi of u. Yeah, so it's being applied on y. So maybe I can make it consistent. Let's call this y, not x. So inside y we call the image dense if the closure of that is everything. Right, so this clearly seems a good thing to understand, to compare x and y, because image may not be everything, but the closure of it is everything, so you have a good understanding, you have a good comparison. That was the point of this rational map definition. We'll be studying dominant rational maps. Okay, let's prove this property first. So say U is an open set and V is a closed set containing U. Then what we will show is that V is everything. How do you prove this? How do you prove that closure of an open set is everything, the whole space? So, yeah, in other words, okay, let me interpret this also. So in Zariski topology, open sets are dense. Okay, so every open set, if you include the limit points, you will get everything. That's what we want to show. So by hypothesis, you have U contained in V. U is open, V is closed. And K also will assume, K will always assume to be algebraically closed. K is equal to K bar. So from this, what you deduce immediately is that U intersection A to the n minus V is empty, right? So you have an open set U and you have another open set complement of V. They don't share a point. Can that happen? That cannot happen, right? We have kind of sketched a proof that intersection of two open sets is always has a common intersection. So which means that one of these has to be empty. The only possibility is that since U we have picked to be non-empty, it means that A raised to n is V. Is that clear? So because of this, Zariski definition actually gives you a topological space where every non-empty open set, the limit points is all that is missing. You get the whole space. Yeah, that's an amazing thing of this definition. We could have also defined closure. Let's do that. So closure of W is the smallest closed set V that contains W, but we have shown above that if W is not empty, then the closure of W is the whole of Y. Okay, so in this in our course, always closure of an open set will be everything. But still the definition of closure makes sense because you can use it when you did not start with an open set. you may start with an arbitrary subset and you can make it closed. Right? So in that case, you won't get everything. But if you made the mistake of starting with an open set, then you will get everything. That's what we have shown. So for arbitrary tableau, we might still use this notation to get the closure. Yes?
What this means is that if I take any closed set in Y and then I take the interior of it and that is empty. That one it's
You take what?
the interior of that set.
The interior.
Any closed set,
No, interior is the set itself.
any closed set,
Yes.
in interior, it should be empty because the closure of that is a whole space, right?
Oh, you are defining interior to be that set minus the limit points. Sure. Yeah, but then you shouldn't even define it because of this, because this proposition gives you empty. Yeah, so in other words, what Rishabh is saying is that in a closed set, if you look at the limit points, it's everything. So the boundary is the whole set. Yeah, so it's a very weird space to be in, which is why all these pictures we draw, they are all false, because I mean in this picture you don't see that, right? You don't see the closure to be the whole Euclidean space. But still they will be good enough to give you actual proofs. Now rational map has a nice computational meaning. With this we can define isomorphism of varieties. So varieties xy are called isomorphic or birationally equivalent that will be the correct term. So we'll call varieties x and y BE if there is a rational map both ways. So if there exists a rational map phi x to y which has an inverse rational map, phi inverse y to x.
Won't it be dominant?
No, it's implied, right? Dominance will be implied. If you have a rational map which has an inverse, yeah. So for now I only say this, we'll say variety is isomorphic or birationally equivalent if there is a rational map from x to y and inverse of that y to x. Remember that this, the way we had defined rational map, it may not hold everywhere, right? You only needed this to hold somewhere on some open patch. So you have to read this with that understanding. I mean, so for all you know, phi is not even defined on the domain X. It's only defined on a patch. So let's see an example which shows you the difference why this was needed. Why did we not stop at morphism? So let's take the example we have been taking many times before, the zero set of x2 square minus x1 cube, and let's take x to be the affine line. So what is the coordinate ring of this? This also we have seen. It's x1 and over kx1 you would go to a finite ring extension, finite degree ring extension, which is, if I call this ideal I, so mod I, and what is ky, big ky, that is make everything invertible except 0, right, localize at 0. So you will get k, this bracket x1 function field, and mod I, which is the same as k x1, and also you have introduced now square root of x1. Actually you introduced square root of x1 cube, which is basically introducing square root of x1. So I can just write it like this. Okay, this is the function field, transcendence degree 1. In fact, it's a pure transcendental extension of k. What happens in this, on this side? So here a of x is kx1 and k of x is just all the functions. So now what you can see is that yeah, I should have said one more thing. Should have given you the algebraic meaning of this rational map definition. What you can immediately prove is that if phi is a rational map from variety x to y, then you can define now homomorphism or a morphism from the field of y to field of x. Maybe I should write it here. So this is a rational map if and only if ky arrow kx is a homomorphism. Why is that true? So this is quite straightforward. You just look at the definition of rational map and compare it with the definition of rational functions. Basically, you take any function f, which will be like g over h on some open patch living in ky, and you can see that through y you can pull it back on x. Okay, because the, say this f equal to g by h was on v, so you look at phi inverse v maybe not here. No, here also it should be possible. Yeah, you can show this. Basically, you pull back the rational function which was on y, pull it back on x, and you will get some open patch on which in x on which it will be defined. The composition will be defined. So just like the morphisms from x to y related to the coordinate ring, the rational maps from x to y, they get related to the function fields. I'll come back to this property again, maybe give a proof sketch, but let's continue with the example. So algebraically we can actually study these maps from x to y. So for that you have to compare ax with ay. So clearly, or you can see that ax and ay are not isomorphic. So there is a morphism from ay arrow ax exists, but it has no converse. Uh, have I messed up the arrows? Yeah, I think I'm messing up the arrows. EY to AX. Yeah, so AX arrow AY is the trivial embedding of this polynomial ring in one variable into two variables, but it has no inverse. Okay, so which means that this Y arrow X is a morphism, that much you deduce. But there is no morphism from X to Y. Right, because if there was a morphism from X to Y, then you have to have a homomorphism from AY to AX. But that actually there is no reverse map.
So this morphism will just be the projection.
Right. Yeah, sure. Yeah, for now I'm only reversing the arrow. I'm not thinking too hard on the geometric picture of this. But KY and KX, they are actually isomorphic. So Kx arrow Ky is actually these are isomorphic. There is an isomorphism. Yeah, they are both isomorphic to the function field Kt.
But isn't that a gate field extension?
No, of what?
Why not x1?
No, so what I'm saying is just this, no? This is isomorphic to K, let's say Y, and so is this.
So what? One is algebraic over the other.
No, one is algebraic over the other, but aren't they both isomorphic to the same thing? So what this means is that the rational map exists both ways. So Y arrow X is an isomorphism. Is that wrong?
The map from Ky to Kx, that is, you just take.
No, but the geometric statement that I am making here is this variety Y birationally isomorphic to the line.
I think you would keep a genus isomorphism.
It's not?
Genus 0. But the thing on the left is a cuspidal curve. So genus, I don't know what the genus is. There is a formula for it.
Yeah, but it's non-smooth.
Yeah, it's not smooth, but it could still be birational.
No, because function fields, if they are isomorphic, then you should have this birational equivalence. Yeah, maybe I should work this out next time if there is some confusion. But these function fields do look isomorphic to me.
The question is, you have k of t,
Mhm.
k of square root t.
Yeah.
This field is isomorphic.
No, obviously. If t is a formal variable, they are isomorphic.
But is it 1 and degree 2 field extension?
No, so
No, these are just formal variables. So,
What is the reverse arrow? I give you k of t, and then I give you k of square root t. What is the isomorphic?
so for any function in K square root t, you just
just associate that function to make square root t replaced by t, means take it square. So you have a function over here. And obviously the reverse error also exists because just saying that you get 2 plus square root t to be a function, then you can map it to 2 plus t.
So the map that you are saying is goes to t, that's the only possibility, right?
Just replace the
It is just the, yeah, it is simply the association. You just associate square root t with t.
just the formal derivation.
Yeah. So in general, when you will have g square root t by h square root t, this will be mapped to gt by ht.
But there is square root t whole square. On the left hand side, that is t. Right?
Mm-hmm.
That minus t should be 0.
Okay.
Then algebraic velocity square root is defined by all. If it's not a algebraic velocity, then square root is all.
No, that key is an auxiliary variable.
No, I think what he's saying is that where does minus square root t go to? That seems to be creating a problem.
No, these fields don't look isomorphic.
Yeah, that is true. Actually, minus square root t has nowhere to go. In the sense that the only place it can be sent to, it should be minus t, but is that a problem? It's not a problem, yeah.
Because these are formal variables, you are just mapping.
Yeah, yeah. Yeah, and in general, as I said before, you just write in this basis variable square root t and map it to a different basis which is t. So this seems to be the isomorphism. So which is why I feel now it's a bit strange, but the variety y is actually birationally isomorphic to the affine line, which you could not have deduced by looking at coordinate ring, but by looking at function field it's possible. Yeah, so this is a more relaxed way to compare two varieties. It gives you something which is actually exactly algebraic, but geometrically it's a bit strange.
Something still seems very strange.
Yeah, maybe I have to come back to this next time. Let me move forward, unless you see a problem by the end of the class. Okay, what I want to define next is what is called an affine open. So we have seen this this object xf, the distinguished open set. We'll also call it now affine open. So we know that this is an open set because it was defined to be x minus zeros of f. F is a polynomial, single polynomial. Right? So it's an open set. We attach this word affine to signify that it can be seen as a zero set itself. So let me try to do that. Yeah, I want to give an isomorphism from this to a zero set. So let's consider the following. consider H to be the set of points in a bigger space with n+1 affine n+1 space like this. So E raised affine n space minus ZF. I want to map this to H as follows. So any point I will map it to. So x1 to xn coordinates will take the point P. I need one more coordinate which is xn plus 1th, which I will just set to be 1 over Fp. Okay, so a point which is which is not a 0 of f, we can actually then invert 1 over Fp. So we are mapping n coordinates to n+1 coordinates like this, and you can show that this map is actually bijective, right? Any point in A and ZF maps to H. It's injective and it is also surjective. So this is a bijection. So in this sense, XF can actually be seen as roots of some system. Okay, so it's a special, so these distinguished open sets are actually special. They are open, but if you expand your ambient space, then you can see them as being defined by exact equations, by equations exactly. So we'll also call XF because of this affine open, because it's like a variety. Although, yeah, the confusion here is that it's not a variety in the affine n space. It was not closed there. There it was only quasi-affine. Yeah, but in a bigger space it is affine. What is its coordinate ring? So that you can see by the definition itself that the coordinate ring of H is simply the n+1 variate polynomial ring modulo the defining system. So that's the coordinate ring, which is nothing but actually localizing the original polynomial ring by f. You have just introduced 1 over f. So this is actually isomorphic to the original polynomial ring of wherever you came from. If it was x, then x localized by f, which is also isomorphic to Ox xf. Okay, so these three things are the same. In the original variety x, let's say embedded in the affine n space, Ox of xf was the same as Ax localized. We have seen this before, and now the third thing we are seeing is this bigger affine space, and H is the affine variety there. And I guess I have set in this example x to be a to the n probably. Let's write that. No, not this. E to the n. It's an example for the whole affine space, but you can do the same thing for any variety. Okay, any questions? So this was just the definition of the same thing, the x sub f, just viewed differently. We have seen before that any variety x has a base consisting of these affine opens. That we have seen before. And okay, let us go through that property I sketched. So varieties xy are isomorphic if and only if function fields are isomorphic. Let's prove that. Where isomorphism, remember, is defined by birational equivalence. So this is the definition of BEQ. It isn't by morphism, but by rational maps.
If we take the definition to be just morphism, I mean x to y you have a morphism and you have an inverse morphism from y to x, then this kx is isomorphic to ky directly follows, right?
Yeah, sure, but
But
many more things will follow. Morphism is far more powerful. I mean, in particular, what will follow? It will be equivalent to ax being isomorphic to ay. It's a property at the level of coordinate rings. So obviously, if coordinate rings are isomorphic, then their field of fractions will also be isomorphic. But you don't want to work with the coordinate ring. Somehow you want, it's easier algorithmically also to work with the function field. Working with rings is a bit harder, or working with fields is a bit easier. So let phi be the isomorphism be the birational map. It's this and its inverse both are rational maps. And yeah, the idea is the same that I mentioned before, that you pick a dominant rational map u phi u and and pick a rational function on the RHS, which is ky. Now what you want is the reverse arrow, right? So going from x to y, you want to go from ky to kx, so you want to pull this back. You want to pull back Vf on x now. So yeah, what is phi u inverse V? Well, so first thing I need is, why should this V be in the image of phi u? Is that clear? No, you don't need the whole thing to be in the image, but just the pre-image, I want to claim that this is open. Is it clear why this is true? Is open and non-empty in X. Why is that? This is the thing which needed some proof actually. In the case of morphism, this was already an axiom, but in the case of rational map, it is not. So you have to prove that this pre-image on any open set is non-empty and open. How do you prove this?
Phi U is a morphism, so
From U to Y. That's all you were given. And it is also dominant.
phi is from U to Y is really considered as B intersection U.
So okay, so we
And U is open in U.
so right, so we have this. This is what we started with. And now V is an open in Y.
B intersection is open in
V intersection what?
U.
No, you can't take intersection.
Phi U.
Phi U intersection. I see.
Is open there.
Did we know that phi U is open?
No, no, but intersecting is the open set, so that's open is defined thing. But
That needs this to be.
no, phi U of U intersection V is open because V is open in Y. That's how it's defined in a small subset.
Okay.
Then by definition, wrong.
Okay, fine. Yeah, so finish that part. This is needed. Yeah, once you have this, you are almost done because now from the RHS you have moved to LHS on over X. So you have this open set in the pre-image. It's non-empty, and on that you can pull back F. So the pullback of F will just be composition, like we sketched in the definition of morphism. So phi U inverse V comma F of phi U. This is a rational function. On X. So it's in Kx. Okay. So what you are essentially doing is it's defined on X because you take a point in X, P, apply phi U, which will take you to Y, and in Y you apply F. And the answer you will get will be in the same field, small k. Okay, so you get a reverse arrow, but it's basically this composition which is doing all the work. And this is how you get a morphism from ky arrow kx. It's a field homomorphism. Okay, so you have this field homomorphism and you have the converse of this, so you have a field isomorphism. So by symmetry you get ky is actually isomorphic to kx. So that is the most interesting case. You go from variety to the function field. The converse of this is a bit easier. Any questions here? I hope you can fill in that detail. Okay, so let's go to the converse. So let's take a field isomorphism ky to k arrow ky arrow kx. Now what this means is that remember ky is actually the field of fractions of ay, which was the coordinate ring, right? So in particular the maximal ideals of the coordinate ring of ay respectively ax, they are in bijection. So this means that psi identifies the max ideals of AY with those of AX. Okay. So at the level of the coordinate ring, you have an association between the max ideals. Now, what do the max ideals of the coordinate ring signify? Max ideal M of AY signifies a point of on Y. So psi identifies points in Y with those in X. Okay, so this was easy. Once you have an isomorphism at the level of the field, you get an association between max ideals, and which means that you actually have association at the level of points. Okay, so Y to X you have this. And I think you don't need isomorphism. For homomorphism you will get similar thing, but the identification will only be one-sided. Okay, so which is why I said that if you have a rational map from X to Y, you get a field homomorphism in the reverse direction. And when it's an isomorphism, then you have algebra isomorphism. So this means that X arrow Y is a birational map. So birational equivalence. Is that clear? So we have defined a lot of things today, but this proof ideas are all the same as we have seen before. None of these proofs are hard. So okay, what we should do is, let's take stock of the situation in terms of the geometry algebra correspondence. So where are we in that picture? So you have the affine n space, and you have the function field now. Big Ka, and this is small k. So in the geometry we think of the affine n space, in the algebra we think of the either the polynomial ring in n variables, or even better is the field of fractions, which is the function field in n variables. And here are the correspondences that we have shown, or at least the associations. So the new things that we have shown are XF, this distinguished open set or affine open. Where has it map in the algebra? It maps to, so remember this, it will not map to polynomials. It will actually map to fractions where in the denominator you are allowed to have anything except f. Right, so that was AXF, the localized. So this is a subset of all the fractions, right? But it's not, it's much bigger than AX. So we have gone beyond the polynomial ring. Okay, so this is the OX functor. OX functor will take you there. For an open set U, OX functor will take you to OXU. So these are the functions defined, the regular functions defined on U. For a point, you will go where? So for a point you will go to the germs, right? That was OXP. So you go to the germs, and what else is there? Yeah, you can also actually look at arrows here. So a morphism, now you take two varieties in the affine n space X and Y. A morphism corresponds to what? Morphism between the coordinate rings, reversed arrow. Okay, so that's the association, and it is both ways. And finally the rational map. So the rational map corresponds to field homomorphism. Reversed arrow. Okay, is that clear? So these are the associations between geometry algebra that we have seen in addition to the old picture. Okay, so yeah, so one nice, one kind of powerful property that we will now get because of this concept of birational equivalence or isomorphism of varieties is that every variety is in isomorphism to a single polynomial equation. Okay, even if you are given the input, it's to your algorithm, the variety is given via a system of polynomials. All those polynomials can be converted to a single polynomial such that this hypersurface that you have and the variety you had are isomorphic. Okay, which is quite a powerful result, and that proof is really comes from algebra. So we can show that that any affine variety of dimension R is isomorphic in the sense of birational map to a hypersurface. Hypersurface in one more dimension, so AR plus 1. Yeah, now this isomorphism will not be, I mean, as you have seen in the definition, it will not be really point by point. It's not that the affine variety and the hypersurface, every solution corresponds to each other. It will only be up to this more general field sense. So field of fractions will be isomorphic, right? So at the level of point, some points there may be a mismatch, right? Because this notion of isomorphism of varieties that we have picked, it's a bit weak. But for all the purposes of the course and also algorithms, it's a useful one. You don't lose too much. So how do you prove this? So let's try that. We'll just see the basic idea of the proof. So consider affine variety X for a prime ideal Ix of the polynomial ring, which is in R variables. This Ix will be prime because variety corresponds to prime ideals that we had seen before. Yeah, so what we defined was mainly this algebraic construction inspired by geometry, localization. Right, so you can localize by a multiplicative set, which means invert, introduce fractions in the set big T, and even more special, you can take prime ideal P, and then the big set T will be complement of this, which is A minus P. That's a multiplicative set. You invert all those elements. That is called localization of a ring at a prime ideal. Localization of A at P. That is how you get these restricted fraction integers. So for example, you can decide that you will divide only by odd B. So you will not have half, but you have everything else. You will have by 3 or by 5 and so on. You won't have by 6, for example, but by 7 you will have. Then there are projective versions of this, and we defined this OX functor. So this is especially good for morphisms. So when you want to compare variety X with variety Y, then instead you should compare OY with OX, and the arrow will be reversed. Okay, so this is a contravariant functor. We'll be using this all the time. We define distinguished open set X sub f for a polynomial. It's basically the zeros of f complement in the variety X, and this can be used to cover any open set that we had seen, and we also saw algebraic version of it. So OX functor on this distinguished open set basically localizes your polynomial ring. It localizes it by multiplicative set powers of f. So 1 by f gets introduced essentially in the ring. And finally the germs are germs of over the variety X at the point P is basically the polynomial ring localized at the maximal ideal, which means that anything outside the maximal ideal can be now inverted, which makes sense because these are nice functions defined around at the point P. The fractions are defined. Okay, so now what we will do is we will define a more, we'll basically relax some of the axioms in a morphism. So this will be a new way to compare two varieties. So this arrow we will call the rational map arrow. The definition will be kind of the opposite that we gave for morphism. So we said that morphism is a map which for any open set V of Y gives in the pre-image an open set and so on, right? Instead now what we will do is we will take an open set U of X and start the definition from that. So for varieties XY, a rational map phi from X to Y is given as, take any set U, open set U of X, and a map defined on that. So U is open in X and phi U is a morphism. Okay, so what we want is we want now to start with the open neighborhood inside X, and we just want a morphism from that neighborhood to y. So it's a more local property than what we had in morphisms before, because morphism was kind of working with the whole of y. Instead of this, now we have whatever the image of u is under phi u, only that part is being used in this. And yeah, this set may be too big because there are, open set U may have a subset which is also open, like U prime and so on. So if we want a notion to compare there, so we mod it out by the equivalence relation with the understanding that if phi U and phi U prime are the same on U and U prime, U intersection U prime, then we call them the same. Okay, so if in a small enough open set you have equal morphisms, then you call these pairs as equal in the set. Something that we have been doing with rational functions all the time, so the same thing, where U phi U is considered equal to or related to formally V phi V if phi U is equal to phi V on the intersection, which is again an open set of X. This is happening in X. Okay, so with that we have these in fact, if we took Y to be X, what will happen? What are these objects U comma phi U going from X to X? So in that case, I think you will recover the definition of rational functions if you are mapping points of X to itself. But if you map from X to Y, where Y is some arbitrary variety, then we call it a. That is true, yes. Okay. Yeah, maybe I should write that. Field meaning that it's a line. A1. Gives back the definition of Kx. Okay, but now this allows us to actually compare two very different varieties. Y may not be a line, may not be the affine line. And we will call this rational map to be dominant if it kind of covers everything in the image. So rational map phi is called dominant if there exists an open U such that the corresponding map from U to Y is dense in Y. So I have to define this term in case you don't know what dense set means in a variety. We basically want to say that it's almost everything. So image of phi U inside Y is almost everything in Y. Okay, in particular if phi U is Y, then we will say that the map phi is a dominant map.
U phi U. Should we think phi U as a restricted map on U or
No, there is no phi. Okay. What is the relationship between phi and phi U? Yeah, you can think of it. Sure, it's a restriction. Yes.
if X is also open in X, then automatically have the phi defined. Then why are we doing so much?
No, the thing is phi need not be defined on all of X.
Correct.
For all open sets, right?
No, no, no.
Only some.
But there is no common,
Not for all.
yeah, so not for all, no, it is for every U.
Then you have phi on X.
It is on every U, but the thing is, what name will you give phi? It's not a morphism. It may not be a morphism. It's just a map.
You're saying for all X is open in X.
Yes.
For all open in X, open in U, we have defined a morphism.
Yes.
So there is phi X entire, and if U is a subset, you're saying that phi U is just a restricted map.
I don't think you want all open sets. It's a morphism on some open set.
No, but the definition is this. I'm looking at all the pairs.
Can't be all. Because then you just have a morphism on X. You want something that is not a morphism on the whole of X.
Okay.
So you want a morphism only on an some open subset U in X.
Oh, so you are saying that it should not be this set.
It should be all the opens.
Okay.
Be some collection of opens over where it's a morphism.
But then just one may be enough.
Yeah, just one is enough. But you still have the equivalence relation.
So what should I say? Some open U. Yeah, this I have to clarify it next time. I see the problem. Yeah, I want this rational map to be much more relaxed than morphisms. So I cannot take U to be X, otherwise it will be the same thing as morphism. Yes, so even if this map is not defined on the whole of X, it will be enough it is defined on, let's say, even a single neighborhood. If it is defined, then we are fine. And yeah, so why does that make sense? I'll motivate that pretty soon. Essentially, there is this idea of dense sets, and even if we don't cover the whole variety, we'll be happy if we are able to cover most of it. So what is the meaning of most? So let's define that. So W, a subset of X, is called dense if the smallest closed set containing W is everything. Okay. So in other words, geometrically, so in the real plane, for example,